Have you ever stopped to think about what's really going on under the hood when an AI model learns, or a video game renders a massive world, or a stock trade happens in the blink of an eye? Well, it turns out the secret sauce, surprisingly, is math. And not just any math, something called matrix multiplication. And today, we're diving into some brand new research that's giving this super fundamental operation a massive speed boost.
So yeah, let's just lay it out there. What could AI, high-frequency trading, and video games possibly have in common? It's this. They are all completely and utterly obsessed with matrix multiplication. I'm not kidding. This one single mathematical operation is a huge performance bottleneck in all these fields. So if you can speed it up, you speed up, well, pretty much everything.
Okay, so let's start with the core issue here, what I'm calling the slow-mo matrix problem. We're going to look at why the way we all learned to multiply matrices back in school is actually, for a computer, just incredibly inefficient.
You probably remember this from math class, right? It's what we call the naive approach. To get just one number in the final matrix, you do a dot product. You just multiply the numbers in a row by the numbers in a column and add them all up. Then you do it again and again and again for every single spot. But here's the kicker. Even for this tiny 2x2 example, you have to do 8 separate multiplications. That number just explodes as the matrices get bigger.
Right, so in computer science speak, this method is what's known as O(n cubed). Now what that really means is if you double the size of your matrices, the time it takes to solve it goes up by 8 times. It's exponential. And as the source material puts it, if you're a programmer, that just kills you to hear. This is basically public enemy number 1 for high-performance computing.
But then, a hero entered the chat. Picture this, it's 1969. A mathematician named Volker Strawson comes up with this clever trade-off, a breakthrough that just completely changed the game.
The absolute genius of Strawson's algorithm is this brilliant trade-off. He figured out a way to get the exact same answer using only 7 multiplications instead of 8. How? Well, he replaced that one really expensive multiplication with a bunch of much cheaper addition and subtraction operations. For a computer, that's a fantastic deal. And that one little change drops the complexity from n cubed down to about n to the 2.8. That little decimal point makes a world of difference when you scale up.
And this isn't just theory, folks. Look at these numbers. This benchmark shows a 512 by 512 matrix multiplication. The old way, almost 100 milliseconds. With Strawson's method, just over 32 milliseconds. That is a 3 times speed up just from rearranging the math. It's incredible.
But, nothing's perfect, right? Strawson's algorithm isn't a silver bullet. It really loves square matrices, and it's happiest when their sizes are a power of 2, like 2, 4, 8, 16, and so on. Plus, that whole trade-off, it doesn't always pay off. If your computer is spending more time fetching data from memory than actually calculating, it might not help. So the hunt for something even better had to continue.
And that brings us right up to the present day. We're talking cutting-edge stuff now. What if you could find the absolute fastest, most optimal algorithm for any size matrix, not just the perfect square power of 2 ones? Well, that's exactly what a new research paper set out to discover.
Okay, before we go any further, there's one word you have to understand to get this: rank. In this context, rank is just the total number of multiplications you need to do. That's it. The whole goal of this new research is to find the algorithm with the lowest possible rank. Lower rank, faster algorithm. That's the name of the game. So how in the world do you find the fastest possible method out of, well, infinity? These researchers built an incredible algorithm they call flip graph search. The best way to think about it is like a giant cosmic GPS. Every possible way to multiply the matrices is a different route on this huge map. This algorithm is smart enough to search that map and find the absolute shortest, most efficient path, the one with the lowest rank.
So what do you get at the end of this crazy search? You get this: a library of algorithms. Now, I'll be honest, when you first look at the files from this research, it looks like complete gibberish. But it's actually a treasure chest, full of these perfectly optimized formulas. And here is the decoder ring. You see these weird folder names like 4 by 5 by 6? They're not random at all. They literally describe the size of the problem. So 4 by 5 by 6 means you're multiplying a 4 by 5 matrix with a 5 by 6 matrix. And inside each of these folders is the code for the fastest algorithm ever discovered for that exact size. It's a toolkit of pure speed. All right, theory is one thing, but what about the real world? Let's talk about the concrete results and what this actually means for the future of computing.
And here they are. The new record column is what these researchers found. In some cases, like the 4x4x5, they shaved off just one multiplication. Hey, a world record is a world record. But then, look at the 5x6x7 case. The old record was 159 multiplications. They found a way to do it in just 150. They just vaporized 9 entire operations from the process. That is a huge leap forward.
Okay, let's get real for a second. There are some important caveats. These super specialized algorithms really start to pay off when the computer is working so hard it can't keep up, when compute is the limit, not memory. On a standard GPU, especially for the smaller matrices you see in machine learning, the old ways can sometimes still be faster. But, and this is a really big but, on custom hardware, like Google's tensor processing units or TPUs, you can literally bake these new, faster algorithms right into the chip itself. And that's where you see just massive, game-changing gains.
So you're probably wondering, how long did it take to find these new world records? Must have been a supercomputer crunching numbers for months, right? Years? Nope. The answer is astounding. It took about 1 day. With a cluster of just 100 CPU cores, they could find a new world record-breaking algorithm in about 24 hours. That is an incredibly small price to pay to push the boundaries of an entire field.
Which really brings us to the final and maybe most exciting thought. The researchers have open-sourced everything. Their search algorithm, their findings, all of it. This field is far from solved, and the tools to make the next big discovery are right there, available to everyone. So the real question is, with a little bit of creativity and some computer time, could you be the one to find the next optimization?